And from now on, we're going to talk about 2, 3, 4 trees. First of all, what is a 2, 3, 4 tree? A 2, 3, 4 tree, sometimes other people say it is 2, 4 tree. Both the names are okay. A 2, 3, 4 tree is a height-balanced search tree. So it is a type of binary search tree. However, the height is balanced. We saw in the last class that an AVL tree was also a height balanced tree. However, 2, 3, 4 tree is another type of height balanced search tree. And 2, 3, 4 trees have 3 types of nodes: 2 node, 3 node, and 4 node. And these nodes give rise to the name a 2, 3, 4 tree or 2, 4 tree. And this 2, 3, 4 tree is perfectly balanced. All the bottom nodes are on the same level. I'm going to show you a picture and it will be clearer. First of all, we need to think about 3 types of nodes. This one is the first type, 2 node. However, this node contains just one element. However, it has left subtree and right subtree. So it has 2 connections to other subtrees. That is why we are calling this node a 2 node. And as in the binary search tree, the values on the left subtree are smaller than A, which is stored at this node. On the other hand, the values on the right subtree are greater than A. Okay, so this is very similar to binary search tree. On the other hand, when we think about the 3 node, we have 2 values. However, we have 3 connections. And the values on the left are smaller than A, and the values in the middle connection are between actually A and B. And the values on the right subtree are greater than B. So this is what a 3 node looks like. And a 4 node contains 3 values and 4 connections. So here we are concentrating on the connections to define the name of these nodes. And as you can see here, the values in this branch are between A and B, and values in this branch are between B and C. And the values on the rightmost subtree are greater than C. So these concepts are pretty simple. Let's move on. And what does it mean by perfectly balanced? As you can see here, all the nodes have the same height. So this one has the same height as the neighbor, sibling. And this one has the same height as its sibling. Okay, so all nodes, all the sibling nodes, or the bottom nodes, are on the same level. This is why we're using 2, 3, 4 trees. In the previous cases, like binary search tree or AVL trees, in this case, binary search tree can have arbitrary depths for all nodes. So it could cause this kind of architecture, and this causes inefficiency. And to resolve this issue, we came up with an AVL tree where the maximum height difference is 1. However, we don't like this. We just want to make perfect balance. And that's what this 2, 3, 4 tree is about. And there are, of course, some operations we can do with 2, 3, 4 trees. And there are 3 major operations: search operation, insert operation, and delete operation. And these 3 operations all take time complexity of O log n. And as you can see, these operations are very efficient. First of all, let's think about the search operation. And this search operation is quite similar to that of ordinary binary search trees. Since the keys are sorted, it is obvious to choose the path following the rule given in the below figure. So this is what we saw. So when we want to find the value, let's say A is 15. However, if you want to find 17 in this node, then when we reach here, we're going to go to the right side because this value is smaller than the value we want to find, 17. And let's say A was 15 and B was like 30. And we want to find 17 again. In this case, we're going to the middle part because this value is between 15 and 30. So as you can see here, in the case of binary search tree, we just had two choices, left part or right part. However, in the case of 2, 3, 4 trees, we have more options. So we need to compare more values. However, comparing values doesn't take much computation, so it does not affect the overall efficiency. So search operation might look very similar to that of binary search trees or AVL trees. And let's move on to insert operation. Insert operation takes place always on the leaf nodes. So leaf node means the bottom of trees. We never insert a new node on the internal nodes. So as you can see here, we cannot insert nodes in the middle of a tree, even if they have room to accommodate. So we are never gonna insert new items in the middle. So how do we insert a new node? We first perform the search operation until we reach the leaf node, because we are going to insert a new node on the leaf nodes. I'm going to describe the process first and then demonstrate how we are going to insert, so don't worry about this. So how do we insert a new item? We first perform the search operation, and if the leaf node is a 2 node, then we can just insert the item and make it a 3 node. Pretty simple. If the leaf node is 3 node, insert the item and make it 4 node. Same as the previous case. So these two cases are very simple. And if the leaf node is 4 node, then we can add more items to this node. And what we are going to do is split this node and then insert. And this could be recursive. And I'm going to show you why it could be recursive in the following slides. All right, I'm going to show you an example. Let's say we want to insert 76 into an empty 2, 3, 4 tree. And because the tree is empty at first, the new node becomes the root of the tree. So inserting for the first time is very simple. We just make a new 2 node, that's all. And let's say we want to insert 85. And because this is the bottom node, we are going to add this 85 to this node. And 2 node becomes 3 node. So as you can see here, the insertion always takes place on the bottom level. And let's say we want to insert 90, then it's going to create a 4 node from 3 node. And let's say we want to insert 52. In this case, because this one is a 4 node, we cannot add 52 here. And what we're going to do? We're going to split these nodes and then insert 52. So we first split this 4 node into this configuration. So what we usually do is make this center node as a parent node, and the right and left ones as children of the center node. And after we split this 4 node into this configuration, and then we're going to perform inserting 52. And where should we insert 52? Now, this is a new bottom level. And 52 should go this part because 52 is smaller than 85. So it should go to the left part. And this is the bottom level. And we can add 52 here. So that's what we are going to do. And as you can see here, the height changed. Height increased, actually. So in this way, we're always adding new items at the bottom level. And here, if you want to insert 20, then it's going to be, because it's smaller than 85, it's going to the left part and comes here. Okay, so insertion is pretty simple. And can you guess what the tree would look like after inserting 33? I'll give you like 1 minute and think about it. All right, let's have a look at what it becomes. First, we need to split. First of all, where should 33 go? It has to take the left part like this, and it should go this part. However, this node is 4 node, and we cannot insert 33 here. And what we are going to do is split this one, and this will become the center node is going to be a new parent, and the left one and right one becomes new child. And we are going to add this architecture to this part. And because this one is two level, and as you can see, 52 and 85 becomes a 3 node like this. And you put 20 here, 76 here. And then we're going to insert 33. And where should it go? It should take the left path and then placed here like this. Okay? So as you can see here, we are always adding at the bottom side. And as we add more and more items, we push some items to new levels, and the height grows in this way. Okay, that was insert operation. Any questions up to this point? Okay, let's move on. And from now on, we're going to talk about delete operation. So up to this point, we've talked about the search operation and insert operation. And the third operation that is very important is delete operation. First of all, the delete operation is a bit trickier than the insert operation. There are a few cases. Let's say the first case is, let's say X is the node we want to delete. And if X is a leaf node, there are going to be several cases. So let's say this is case 1.1. X is in either 3 node or 4 node. In this case, we can just delete X and there is no height change. And the tree is perfectly balanced. And if X is a 2 node, then underflow occurs, meaning that the height of that node, the height of the nodes that contain X will change. And this causes some problem called underflow. And if X has some siblings, and the sibling of X is 3 node or 4 node, we are going to steal some items from siblings and then perform deletion. So let's have a look at this. Let's say we want to delete, let's first think about we want to delete 33 or 20. Then because this node is 3 node, we can just delete it and nothing we need to do more. However, if you want to delete 76, if we delete this one, then this one has a hole and the bottom level is not full any longer. And that is what underflow is about. And what we want to do is always make the bottom level full. That is perfectly, that is what perfect balance is about. So what we want to do is make the bottom level or keep the bottom level full all the times. That's what we want to do. However, if you delete 76, then it's going to create a hole. And how are you going to deal with that? If its sibling, this one or this one, is 3 node or 4 node, then we're going to steal one item from its sibling. So first of all, we're going to rotate. So 33 goes up and 52 goes down. And then make this node as 3 node. Then we can delete 76. So that's what we are going to do, like this. Okay. So if sibling is 3 node or 4 node, we're going to pop one of the items of the sibling to the parent and then get one item from the parent and replace it with the deleted one. So if you compare these two cases, you just pop one item from sibling to the parent and replace the 76 with one of the parent, like this. Okay, that's what we do. And if we are stealing from the left sibling, then we get the left one. And if we steal from the right sibling, then we're going to get the right one from the parent. Okay. And let's say if siblings are 2 node, but the parent is either 3 or 4 node. In this case, what we can do is, let's say we want to delete 90 in this case. However, its sibling, which is 76, is just 2 node. However, the parent has 2 items. So what we are going to do is, We cannot steal from our sibling because it is two node. And what we are going to do is merge these three parts. So itself, the parent, one of the parent, and its sibling. Then we can delete 90 like this, because this is the case 1.1. All right, so this is the deletion process. So you need to think about several cases like this. And what happens if both sibling and parent are two nodes? This could only happen when the parent is root. I told you that we are always inserting at the bottom level, and insertion, it cannot take place at this internal node. And because we are inserting in this way, this case where siblings and parents are both two nodes can only occur when parent is root. In this case, we're going to just merge these three items and then delete 76 like this. Okay. So that is the deletion operation when X is in a leaf node. However, we sometimes want to delete when X is in an internal node. How can you delete a node that is an internal? What we are going to do is we're going to find the predecessor, the leftmost leaf in the right subtree of the node containing X. And the predecessor is always a leaf node. And this is what we did for binary search tree and AVL trees. And as you can imagine, we're going to replace the two nodes. So exchange the node containing X with its predecessor, which is the leftmost leaf in the right subtree. So this is equivalent to moving the node containing X to the leaf node and then delete that node. And we saw how we can delete the leaf node in the previous slide. Now X is a leaf node. This is the case 1. And we're going to use the rules given in the case 1 to delete it. So in summary, we are reducing the case 2 into case 1 by replacing the item that we want to delete with the leftmost leaf in the right subtree, and it's going to become case 1. Okay, and now we talked about the properties and the operations of 2, 3, 4 trees, and we need to implement 2, 3, 4 trees. However, the problem is the implementation of a 2, 3, 4 tree is not very straightforward. We saw that there are 3 types of nodes, and there are frequent switching. As you saw in the previous slides, we need to move nodes from bottom to top, top to bottom quite a lot when we are both inserting and deleting. And these properties make implementation very complicated. And an equivalent data structure of 2, 3, 4 trees is called a red-black tree. So because 2, 3, 4 trees are very difficult to implement, computer scientists invented an equivalent red-black tree, and they are going to use red-black trees instead of 2, 3, 4 trees. And being the binary search tree, so 2, 3, 4 trees, AVL trees, red-black trees, all of them are binary search trees. And red black trees are much easier to implement. In fact, red black trees are easier to implement than 2, 3, 4 trees. However, red black trees are much more difficult than AVL trees to implement. So up to this point, we talked about the definition of 2, 3, 4 trees and the 3 operations: search, insert, and delete operations. Any questions up to this point? Okay, let's move on. What is a red black tree? We are going to convert 2, 3, 4 trees into red black trees as follows. We are going to make 2 node into a black node. And for 3 node and 4 node, what we are going to do is 3 node becomes a pair of black and red node. And we are going to make one of them black, and you can choose any of them. However, we prefer to make the left one as red one because we want to fill the left part first. So what I mean by this is when we have some places, so empty places like this, and we want to fill in the left part first. So that's why we prefer this conversion to this conversion. And 4 node becomes this architecture. As you can see here, the middle one, the center node, becomes the black node, black parent node. And the left and right siblings becomes 2 red children of the center node. All right. And it doesn't really matter how you color the edge. However, the convention is the edge follows the color of the connected node at the bottom. Okay, so it's not very important. The important thing is the color of the nodes. The edge color does not really matter. All right, I'll give you some time. And can you convert the following 2, 3, 4 tree into a red black tree? Think about it for like 3 minutes and send me your answers. However, it is quite hard to send your answers. So let me know the black nodes. Okay, so think about it for like 3 minutes and send me the black nodes. All right, thank you for sharing your answers. Let's check the answer together. This is the structure. So the two nodes becomes black node. This one, this one, this one, this one, this one, this one, this one. And then this should be always red node. And between these two elements, I told you that we prefer to make this one as black node. However, both of them can become black nodes. And in this case, we prefer to make this one as black node. However, it doesn't really matter. But when we're implementing, we prefer to make the right one as the black one, black node. Okay. And there are some special properties of red-black trees. The first special property is called root property. It means that the root should be always black. And there is another property. There was one question. I don't understand your question. What do you mean by same children should have same black or same red? Yeah, that's correct. What you describe is correct. I'm going to describe that in the following slide. All right, that was a good question though. So the first property was root property, where the root should be black. And the external property signifies that every external node is black. And I defined the term external or internal nodes quite vaguely in the previous slide. However, in the next slide, I'm going to define external and internal nodes explicitly. Anyway, external nodes should be always black. That is the second property. And the third property is internal property. The children of a red node are black. This is very important. So what it means is after red node, there cannot be one more red node. So there should be no two consecutive red nodes. So as you can see here, after red, there cannot be another red following, or this cannot be red. However, the sibling can be either red or black. It doesn't matter. However, in the relationship between parent and child or children, two consecutive red nodes can occur. So this is the internal property. And the depth property, this is also very important. All the external nodes have the same black depth, defined as the number of black ancestors to the top. So why? Because we converted 2, 3, 4 nodes into red-black trees. And one of the most important properties of 2, 3, 4 trees was that all bottom nodes are perfectly balanced or full. All bottom nodes are full. So external nodes should have the same height or same depth because we're converting 2, 3, 4 nodes into red-black trees. And we just need to count the number of black depths to the top. So when we reconvert these red-black trees into 2, 3, 4 trees, then all the bottom nodes are going to become full if you follow this depth property. So you need to keep in mind these two properties when we are describing the insertion or deletion operations for red-black trees. So in the previous slide, let's say this node takes 1, 2, 3 black nodes to the top. And this one also takes 1, 2, 3 black nodes to the top. And I'm going to describe the external nodes. And these empty nodes are external nodes. And this one also takes 1, 2, 3 black nodes to the top. So all the bottom nodes or external nodes have the same number of black nodes to the top. So that is what depth property is about. So up to this point, we defined red-black trees and some properties of red-black trees, RB trees. Any questions up to this point? All right, let's move on. First, we're going to talk about the insertion operation. First of all, we need to define two types of nodes. As I told you, there are external nodes and internal nodes. External nodes are nodes that do not have any children. And in the previous classes, we defined node class. And when we're defining node class, we defined self-right as none by default and self-left as none. And these non-nodes are actually external nodes. And internal nodes are nodes having one or more children. And here, we are actually omitting the external nodes. However, in our implementation, we're going to put non-nodes here, and here as well. So in this figure, the external nodes are omitted. However, they are actually there, even though we have not depicted, okay? So this one has a set of these external nodes. So these non-nodes are external nodes, and all the other nodes, whether they are black or red, they are internal nodes, okay? And I'm going to describe the overall process of insertion for red-black trees, and then I'm going to show you on a concrete example. So to insert a new item to a red-black tree, what we do is first perform the search operation and find an external node. Because in the case of 2, 3, 4 nodes, when we are inserting, we always looked for a leaf node. And on the leaf, we inserted that new item. And because we did that for 2, 3, 4 trees, we're going to do a similar thing. We're going to do a search operation to the bottom and find an external node. And this external node is at the bottom of this red-black tree, or the corresponding 2, 3, 4 tree have it on the bottom. And what we are going to do is create an internal node. Let's say Z is what we want to create with 2 external nodes and place Z there. So after this node has Z, we need to create 2 non-nodes, okay? And if Z is root, then we're going to color Z as black. However, if Z is not root, what we do is we first make it red. And if Z's parent is black, then everything is fine. We need to do nothing more because all the properties we described are satisfied. However, if Z's parent is red, then as this internal property signifies, we cannot have two consecutive red nodes. So here, when this parent is red, something called double red problem occurs. And we need to resolve this problem because we have two consecutive red. And I'm going to describe the remedy for the double red problem. And how can you fix this? Before we talk about the remedy for the double red problem, we're going to define some notations. Let's say Z is the node we have just created, and it is red. And let's say V is the parent of Z, and it is also red. Because these two are red, the double red problem occurred. And let's say U is the parent of V, and W is the sibling of V, another child of U. So Z here, the parent of Z is V, and the parent of V is U, and another sibling of V is W. So this is the configuration. And V is red, R is red. Okay, so we are considering this situation. And there are also several cases. First of all, sibling W of V can be black or non-node. So external nodes are black. So it could be either a node containing some values or a non-node. This means a malformed 4-node of a 2, 3, 4 tree. And we perform restructuring. And there are 4 subcases. So I told you that Z and V are red, red, like this. And the parent of V is black. And the sibling is, because this one was originally red, it cannot be red. This kind of situation does not occur because originally this tree was red, black tree. And the situation where U is black is not possible. So W is black. And in this case, this one is just a malformed 4-node. And we can just restructure into this form. So now 20 becomes the new parent as black. And then 10 and 30, Z and V, U becomes new child like this. So we can do, in these 2 cases, we can do just single rotation to reach this configuration. And these 2 processes requires double rotations to reach this configuration. And we saw how we can implement rotations in the AVIA class. And the case 2 is when the sibling W is red. And what does it mean? This means overflow. It is a 5-node. And we're going to perform something called recoloring. So this is the case. D was red, V was red, and the sibling of V is also red. And this corresponds to this case, 5-node. And when this happened, what we did was, before inserting 10, we splitted this node. So 30 goes up, and 20 and 40 stays here. So 30 here, and 20 and 40 stays together. And then we can put 10 here, like this. So that's what we are going to do. So we're going to pop 30 and make it go one stage up, one level up. And we're going to make this configuration. So after coloring 30 from black to red, make 20 and 40 as black. So we just recolor these nodes, then we can resolve the double red problem. However, this recoloring could cause another double red problem. If this happens, then we continue going up the tree and resolve all the double red problems. We perform recoloring until we finally resolve the double red problem. That's just what we need to do. So case 2 is pretty simple. What we need to do is just recolor, change the color of nodes. Then we can resolve the problem. So this was insert operation. And we're going to talk about deletion. As before, I'm going to describe the overall process first and going to show you some examples. What we do is perform the search operation and then find U. Let's say U is what we want to delete. And if U has 2 internal children, then find the first node in the right subtree. So it is going to be leftmost node in the right subtree. And let's name it V. And we're going to replace the value of U with that of V. So we're replacing, exchange U and V, and then going to delete U. So U goes to the bottom before it gets deleted. This is what we do for BST or AVL tree or 2, 3, 4 trees. Okay, then remove V. Therefore, we don't need to think about other cases, but we just need to think about when V is a node that has 1 or 2 external child, W. So that's the only case. Because when we want to delete some middle item, what we do is we find the leftmost item here and then exchange this node, U and V, and delete this node. And because this one is the leftmost child in the right subtree, this one has 1 or 2 external nodes. Okay, so this is the only case we need to consider when we are deleting. And I'm going to show you a picture. Let's say we want to delete this V node. And V has a parent, X, and V has 1 external child and 1 sibling. And this could be also external. And what we do is we remove these 2 nodes and then connect X and R like this. That's all we need to do. So this is the picture for recap. If V is red or R is red, that means when V is red, then R is black. When R is red, that means V is black, because we cannot have 2 consecutive red nodes. Okay, so this was the case. If this was the case, we're going to just make R black and we are done. If you think about the depth property, is satisfied if you just color R as black in either of these classes, these two cases. However, if R is black and V is black, we have two blacks. However, we are removing, we have two blacks, R is black and V is black, and we're removing V. Then the children of R had originally the black depth to the top, say N. However, because we removed this one black, now it becomes N-1 black. And this violates the depth property. And we need to fix this problem. And we call this problem a double black problem. And this corresponds to the underflow situation of 2, 3, 4 trees. And before we resolve this issue, we're going to mark R as double black because it should have one more black. And let's have a look at the remedy for the double black problem. The case one is sibling Y of R is black and has a red child Z. This means we need to steal something from its sibling in the case of 2, 3, 4 tree. And we are going to perform restructuring, single or double rotations. Then we can resolve the issue. And then we're going to perform recoloring. So let's say we removed this node and we have a right child like this and the sibling. And this corresponds to this situation. These two connections means fictitious double black. And we need to resolve this double black problem. And I colored this one as yellow because it doesn't really matter. It could be either red or black. It doesn't matter, okay? And what we are going to do is, and there is another case where these two configurations are possible. In the first case, we are going to perform single rotation. And in the second case, we are going to perform double rotation. So we are going to steal this one and pop up 20 of the parent. This is what we are going to do. And this corresponds to this configuration, new configuration. So we are performing single rotation or double rotation to make this configuration. And we make 20 as the new parent and color it as red. And other nodes become black nodes. So this is the case one. And this corresponds to stealing of a 2, 3, 4 tree. And the second case is when sibling Y is black and has no red child. And this corresponds to fusion of a 2, 3, 4 tree. We just need to perform recoloring. That's all we need to do. So this is the case. In this case, we are going to perform fusion, and this 40 is double black. So to resolve this issue, we're going to make these nodes become one node. And this corresponds to this situation. And as you can see here, what we do is just turn this red node into black node and turn this black node into red node. That's all we need to do. Okay? So this was the case 2. And the third case is when sibling Y is red. In this case, we're going to do restructuring and recoloring. Y is black, X is red. Then case 1 or 2 reappears. And we can apply the rules for cases 1 and 2. So the example is like this. Sibling Y, this one, is red. So how can you resolve this issue? We're going to restructure first and then recolor. So we make this structure into this one. And Y becomes red here. And X becomes, which was originally black, red. And when you check the corresponding 2, 3, 4 case, these structures are the same. However, because we can have multiple representations of red, black trees for the same 2, 3, 4 tree, we're just turning this one into the forms that we know, cases 1 and 2. And we are going to apply the same rule for cases 1 or 2 to resolve this issue. So that is deletion. Okay. So up to this point, we talked about red, black trees and 2, 3, 4 trees. The motivation of 2, 3, 4 trees was to make the bottom level full. So we can always have the balance, perfect balance. And as I told you, the ordinary binary search tree, the height is not balanced. In the case of AVL tree, height is balanced. However, there was some difference of height between nodes, and the maximum difference of height was 1. And in the case of 2, 3, 4 trees, we're making full balance. All the bottom nodes have the same level. And because these 2, 3, 4 trees were quite hard to implement because there were frequent switching of nodes. And what we do is creating red, black trees, which is equivalent to 2, 3, 4 trees. However, easier to implement than 2, 3, 4 trees. So we talked about 4 types of binary search trees. So summary is we discussed the concept of 2, 3, 4 trees, and insertion occurs at leaf nodes, and we split when overflow occurred. And deletion sometimes causes underflow. Then we steal or fuse some nodes to resolve this issue. Plus, we talked about red, black trees. We could think of the equivalent 2, 3, 4 tree architectures for insertion and deletion. For insertion, we had to deal with the double red problem. And for deletion, we had to resolve the double black problem. This corresponds to overflow and underflow. In fact, modern languages utilize red, black trees for implementing dictionaries. So Python internally uses red, black trees to implement the dictionary we are using. And in other languages, they do not call this data structure as dictionary, but they call it map. So when you use Java, they say map data structure rather than dictionary. So when you're using other programming languages in the future, you may see map quite a lot rather than dictionary.